I just remind starting that this is a seminar series of the World Department, and in particular, I also thank the help of the administration and of the IT, so thank you for being here streaming and recording. And also to all of you, since it's a series of the World Department, please, if you have suggestions, just contact any person of the committee, and of course we're happy to discuss the future plans. And it is my special pleasure to welcome Professor Yann Brenier, who is currently research director at the CNRS. And okay, thank you. And in Paris, and he is emeritus professor. And he obtained his PhD back in 1986 from Paris Dauphine. And since then, he had an illustrious academic career, holding several positions in prestigious institutions, for example, at the University of California, in various institutions of CNRS. Now he's in Orsay. And for example, he was also professor at the University of Paris 6, assigned to the École Normale. And among his distinctions, I mentioned that he has been member of the Institute for Advanced Studies and a junior member of the Institut Universitaire de France. Please correct my pronunciation. And he has received various awards and honors, including being invited speaker at the ICM in Beijing. And his research spans various fields of applied mathematics, I would say focusing primarily on PDEs and numerical analysis. As you will notice, he likes problems from fluid mechanics and plasma physics, tools from optimal mass transport, I just mentioned. He has published a high number of research papers, I believe more than 100, but okay. I just mentioned that he had various students, 10 at the doctoral level, and they have great position both in the academy and also in a extremely high-level bank. I don't pronounce the name, but I don't want to advertise it. Among his various contributions, I just mentioned the polar factorization theorem and the Benamou-Brenier formula, just because I particularly like them. He has delivered various prestigious lectures worldwide, for example, in Chicago, in Maryland, in Bonn, in Berkeley. Okay, I don't list all of them because otherwise it's endless, but it's really an honor to have you here. And so join me in giving a warm welcome to Professor Yann Brenier.
Thank you very much for the presentation. It's a great honor for me to be here in Padova, because I mean it's the University of Galileo, you know. It's a very impressive place. Okay, and I will talk about relationship between fluids. So you said that I like fluids, but I don't like to fly, and I don't like to be on the boats. So I'm very careful about fluids. However, so I prefer trains. However, I like some mathematics related to fluids, and as we will see, the connection with some combinatorics, I mean permutation. And this will be a way to talk a little bit of optimal transport, which is a very lively field. Let me start by giving an outline of the talk. Okay, so I will start by mentioning the contribution to fluid mechanics by Leonhard Euler. After that, I will discuss the the geometric approach given by Vladimir Arnold in the 60s, 1960s, for the Euler equation of incompressible fluid. So I will stick to incompressible fluid in this talk. So water, if you prefer. I mean, essentially water. And then at some point, I will indiscrete a kind of discrete version of the incompressible fluid mechanics, which will involve permutation. So this is what I call discrete fluid motion. And also, there is a related concept of generalized flow that will come up. So after that, we will see some discussion about combinatorial optimization, which leads in a very natural way to the discrete version of optimal transport. Okay, and in the last part of the talk, I will mention some recent activity about connection between incompressible fluid and gravitation, and it's an idea that came up to me a long time ago, but it's getting realistic in the sense that this is now work with some people of the Institut Astrophysique of Paris. So there is a really people doing cosmology which are involved in this work. So, which is good to know. So I mean, I like this picture, which is I think taken from the US series, The Big Bang Theory. Sometimes there is the main character, Sheldon Cooper, has a T-shirt with this picture. I don't know where it comes from, but it's a very nice illustration of the purpose because you have a melting Rubik's Cube, so it's really combinatorics to fluid. Okay, at least in that direction, going back, it's more difficult, I guess. And also this nice stamp of Euler, which, as you can see, he was from Basileo or Basel, and he is a Swiss, maybe one of the most famous Swiss person ever. And another portrait with this beautiful formula about probably one of the first abstract mathematics formula ever, like an index of something, which is very beautiful. And also, of course, you know that Euler is very famous for the contribution to number theory. And actually, the Riemann zeta function was really introduced by Euler, which is this harmonic series. And this beautiful relation, I think it's one of the most beautiful formula I know in mathematics, because you have the list of the prime number popping up in this product formula. I think it's beautiful, actually. It's incredible. And but now I will concentrate on something which is not necessarily very well known, at least in among our colleagues in algebra and geometry. They are not so much aware how important is the contribution of Euler to fluids and PDE. So to fluids, because actually in the same paper that I will show you some pages in a moment. In the same paper, which is from 1755-57, he has, in some sense, the first field theory in the history to describe fluids. So that means you describe completely a physical phenomena by a set of PDEs. And at the same time, as far as, if I'm not mistaken, this is the first multidimensional evolution PDE ever written at once. So in the same paper, and they are nonlinear. Okay, so it's a fascinating paper, and and also for me it's very nice. It's written in French because it was for the Academy of the Royal Academy of Science in Berlin, and the King of Prussia, Frederick II, said that German is not ready to be a scientific language, so everything should be written in French. Okay, maybe Latin was accepted also. I don't remember. Anyway, so you have this evolution equation, and they are almost written in a modern way. And this is remarkable because in the 18th century, it's not obvious to recognize a PDE. For instance, D'Alembert wrote the wave equation in 1D, but it's very hard to understand the notation. But you know, the notation of Euler are almost the same as the one you will use. So you have the velocity of the fluid is described by U, V, and W, the three components of the velocity. The pressure is still denoted by P. The density is denoted by Q. The coordinates are denoted by T, X, Y, Z. So nothing to change. And so this is the equation describing how the acceleration of the fluid is related to the pressure field. And this has to be completed because this is not comprehensive to do that. So you have to complete that by what people call the continuity equation. Actually, in the language of Euler, it's équation de la continuité. So which relates the evolution of the density of the fluid according to the velocity. And in the paper, Euler is talking about both the incompressible and the compressible fluids. And in the incompressible case, like water in ordinary condition, he mentioned that you have to use this divergence-free condition for the velocity field. So this is pretty clearly explained in this paper. Very nice. So, okay. So the conclusion of the paper is quite astonishing because it says, well, you know, in some sense, I did my job to write down the equation. But these equations are difficult to solve, and the analysis is not advanced enough to do it now. So I leave that to the people after me. And I could say that 250 years later, it turns out this PDE looks very simple, but it's one of the most challenging PDE, I mean, for experts in PDE. It's really, we don't understand very well this equation. So they are both the first equation and one of the most challenging equations after a quarter of millennium. So I think it's quite fascinating. And also, you may know that the fluid equations are related to something which is very difficult for physicists, is hydrodynamic turbulence. In some sense, this is one of the most mysterious open problem in physics to understand hydrodynamic turbulence. Because we know, I mean, they know a lot of quantum mechanics, of general relativity, but actually, I vaguely remember, maybe you don't know better than me, there is a joke about a physicist who died, and he's a good guy, so he goes to heaven, and he can meet God in the sky, and he's allowed to ask two questions to God. And the first question is, can you write the equation of everything for me? You know, the equation, oh yeah, it's very simple. And God is just writing the equation on the blackboard. And the second question is, oh, can you explain me how the turbulence of fluid works? And say, oh, no, this is not too difficult for me. Yeah. So I don't know, I mean, it's supposed to be a classical joke, but I don't know exactly who introduced this joke. Okay, so now this is a conclusion. Sorry, it's written in French. And if you understand French, he says exactly what I said, that the principle of mechanics are not missing because I wrote the equation correctly, but the analysis is not cultivated enough in order to solve this equation. And then this will be the future of the field. And this was 250 years, more than 250 years ago. Okay, so now I would like to move to the second section about the geometry of Euler equation of incompressible fluid, and it's a rather famous contribution of Vladimir Arnold, who wrote a quite well-known paper in the Annals of Institut Fourier in 1966. Actually, by chance, it's also written in French. I don't know why. But, and he made a kind of precise observation of something which was more or less implicitly in the paper of Euler, in the sense that Euler had the intuition that his model for incompressible fluid can be derived from the least action principle. And therefore, in some sense, Vladimir Arnold explained more precisely that the motion of an incompressible fluid can be translated as the equation of a geodesic curve, but not on a finite dimensional set, on an infinite dimensional group of volume-preserving diffeomorphism of the domain in which the fluid evolves. So assume that the fluid is just evolving in the container, nothing exists, nothing enters. And then he said, well, the movement of the fluid, there is no external force, will be just following a curve along all possible configuration of the container, which are volume preserving, because it's incompressible fluid. So it's a very simple-minded principle that can be worked out. And it's equivalent to the Euler equation. Okay, so maybe just to show you that the configuration space of volume preserving map is not a trivial stuff. So here I use not a domain in R3, but just the flat torus in 2D, so the periodic square. And I show you 3 different maps of the square. So I just put a grid on the 2 torus, and I show the deformation of this grid by the 3 different maps. And of course, the fact to be volume preserving is not trivial, because only one of the 3 maps is volume preserving. So since we are in 2D, volume preserving means area preserving. And so, of course, you see that only the last one is really area preserving. Because you see here, for instance, here you have a big distortion, contraction, here also, and only this one, you know, the area of each box is the same. And therefore, the incompressible fluid navigates along this kind of maps. And this is a very strong constraint. So the geodesic, this creates some curvature, and the curvature, just like a geodesic on a sphere, is curved by the sphere itself. So it's curved, and the curvature is described by the pressure field. The pressure field is really the output of the curvature of this infinite dimensional set. So this is the Arnold interpretation. So now, the combinatorics comes up, because if you think in a discrete way, a little bit like when you are using pixels on the screen. So in some sense, by graining the space, what is equivalent to the concept of volume preserving at the level of pixel is permutation. Because permutation, you just respect the volume. Of course, it's not a diffeomorphism anymore. It's a much rougher type of map, but this is the idea. And therefore, this is what I'm going in this third section. It's to consider, if I have my domain D, to consider, it's a little bit like this old game, which is probably old-fashioned, where you have to, where you play around with moving in a cube with permutation. Of course, it's more complicated than that, because you remove one and, okay. But I guess, I don't know, you heard about this game. Maybe, I don't know if it exists anymore. Or maybe there is a computerized version of it now. Maybe on the cell phone, on your smartphone, maybe you have that. Okay, and therefore, the idea is instead of have a continuous deformation of the space, you just use permutation of this box. Okay, so for instance, just to give you a drawing and an example, let me consider instead of making the fluid in a square, let me consider that it's just a tube. A little bit like a pipeline, like a pipe. And therefore, so it's more or less almost a one-dimensional object. So I cut my pipe in 12 different sections, and now I define a discrete flow just as a permutation, a time-dependent permutation of these cubes. Well, they are not cubes because these rectangles. And the time, of course, I mean, it's natural thing to consider that time is also discrete. So everything is discrete. It's totally discrete. So for instance, this is just an example. So for instance, I can decide to exchange the 2 neighbors like this. So this will be my first time step of the evolution. And well, if I do that again, I will go back to the previous situation, so it's not so interesting. So maybe I can decide to fix the endpoints and to do the permutation between 1 and 4 now, and 3 and 6, and so and so. So I get something like that. You know, I fixed the endpoint, and I can continue. So at the moment, this has nothing to do with Euler. I can play this game, and for instance, I can tag some of the cube, for instance, 4, and you see the evolution of 4 is going to the left like this, going back to the right. 5, which is a neighbor, is going to the opposite direction. And here, because in some sense I decided to speed up a little bit the motion, so it's a little bit boring to move just one step by one step. So let me just do that. Why not? And that's a possible configuration. Well, okay. So this is an example of a discrete flow with a 7 time step and 12 cells. However, this has nothing to do with so far with the Euler equation, because I didn't give you any rule about the motion. So the idea now is to try to minimize, to see whether you can minimize the cost of this motion. And so the way of computing this is exactly the same thing I had before, but now I put some kind of a metric or a cost on this flow. And the right thing to do is to consider the sum of the square of the displacements. The sum of the square of the displacements. And there is a natural unit length, which is just, you can say that this displacement from 1 to 2 is just 1. And you see that if, with the example I gave to you, when you do the computation of the total cost, we get 108 centotto in this unit. And you see that in this strange step where I did this jump from 2 units, this cost a lot, because this single step, you know, the first step was 12, because I have a 12 cube moving. The second step, because I fixed the endpoint, is 10. So the cost from here to here is 12, cost from here is 10. And here it's terrible, because I have 2 to the square, because I square, it's the sum of the square. And therefore, you see that in this step, the cost is 42. So in the total cost, almost half of the cost is due to this extravagant motion where I decided to jump by 2 units. So in some sense, you feel the importance of minimizing the square. This prevents you to do big jumps, you know, because they are very costly. And so, in some sense, a discrete geodesic, a discrete minimizing geodesic will be defined as 2 permutations. So the first one is the trivial permutation, and the last one, a finite number of time steps, and you try to minimize, among all possible discrete motion, the sum of the square of the displacement. And this is exactly playing at the discrete level the same role as the minimizing geodesics in the continuous level. So in some sense, it's a fully discrete version of the Arnold-Euler principle, if you want. And we are going to play with this a little bit. So you see, the last step costs a lot. Okay. Of course, a very naive way, say, well, I mean, it's a finite problem, because you know you have a finite number of permutations. So it's not so difficult to do. But unfortunately, even if it is a very crude problem, you have already 10 to the 52 configuration. So it's you need combinatorial optimization. You cannot do that by just checking all possible configuration. You will never find a discrete geodesic this way. So you need algorithm for that. Okay. And therefore, if we are lucky, by understanding this discrete model, maybe we have some chance to address the continuous limit, which would correspond to the motion of incompressible fluid motion, the motion of water, according to the model of Euler. And actually, following this idea, well, I was involved at least already 30 years ago in the understanding what you can do at the continuous level based on the intuition given by the discrete. So in some sense, the game is not to really to understand the discrete problem, but just to understand how the discrete problem lead you to a fresh view on the continuous problem. And so I was involved in that, and the method to address the continuous limit are very much related to convex analysis and probability measure. A little bit like optimal transport that we are going to see later on. And so there was a series of errors, and I was very glad that actually when Alessio Figali was completing his PhD, this was a part of his PhD, he was revisiting the theory and improving the theory actually. So, okay. So I think it's we're together with Luigi Ambrosio. And for instance, now let me go back to the discrete level and let me try to see, because this was exactly I started really my theory by doing this. So I was thinking of the following problem. So assume that I start from this situation. I want to reverse the order of the cube. So can I find a kind of an optimal discrete solution without, of course, looking at all possible configurations, just by simple problem, and maybe I can pass to the limit. And well, you already saw the idea before. So the idea is to exchange neighbors, and every even time step, you fix the box at the end point. Okay, and so you can do that. And it turned out it works. So for instance, well, it's hard to read. So in some way, if you do that, you see, for instance, here I exchange two neighbors, but at the second step, I fix the end point, and I do that again. And slowly, I will go to the zero configuration. And if I tag two neighboring points, 4 and 5, it's very clear what happens. So the cube number 5 is just moving to the left, hits the boundary, it's reflected back to the right, and the number 5 does the opposite, goes to the right, bounce back to the left, and actually you can notice that the final step is missing, 12, 11, 10, but actually if you do the permutation at the very end, you get exactly the final configuration, and 4 and 5 will be just, again, neighbors in the symmetric situation. And then the good thing about this discrete heuristic, it's very easy to pass to the limit. Okay, so this is a mistake, a typing mistake, but I think it's nice looking. So there is actually there is a missing slide, but I decided to keep it. It's nice. So is it because this is it's very easy to pass to the limit. And you see when you pass to the limit, you know now you get back to the continuous setting in space and time. You assume that you have zillions of points and zillions of time steps. But we see that the limit is very clear. So every point splits, because 4 and 5 were just neighbors. So in the limit, it's just the same point is just splitting in two parts, one going to the left, one going to the right, a little bit like the wave equation in some sense. So you have and then by symmetry, and the ending point is exactly the symmetry. So in the initial map is x is x, and the final map is 1 minus x on the unit interval. So reversing the orientation. And then for a while I said, well, and I can do that for every point. So for every point in the first axis, I will have a splitting of the particle in two with this. Of course, it cannot be described by even by diffeomorphism. So it's a kind of some people in calculus ovation call that a Young's measure. So in some sense, you have from a point you generate 2 points, and in more general way, a kind of probability measure. So this is the idea. And for a while, I was convinced that that's the optimal solution. And actually, it's not. And you can reduce the cost. You can compute the costs. Well, of course, you do to the limit. And you can reduce the cost by, you can save a little bit of energy by doing the following. So here I just draw the picture only for 2 points. So the initial point is x, and the final point is 1 minus x. It's the symmetric point. And instead of 2 trajectories, which was my guess at the beginning, so I have a continuum of trajectories. So of course, I draw only a finite number of them, but it's a continuous family of trajectory, which are very smooth. And actually, all of them are sinusoid. And they are connecting x to 1 minus x. And you do that for every point. So you have what I call a generalized flow. So it has nothing to do with the standard description in terms of diffeomorphism. Because for every point, you have a continuous family of trajectories. And they are on top of each other. And in some sense, this is volume preserving in 1D. That is, in some sense, they fill the space uniformly. And in this theory that I developed, actually you can make, so I don't put the mathematics because it's too heavy, but you can really show that this solution is optimal in some setting. So typically the setting, it will be like the setting of probability measure on path with the constraint that the projection of this probability measure on path at every time is the uniform Lebesgue measure on the domain you are looking at. And so you can make a precise, and it's not very difficult. And it turns out the problem of minimizing geodesics, in that case, becomes a convex minimization problem, which is strange because usually a geodesic problem is very far from convexity, you know. So it's not a convex. For instance, you have geodesic on a sphere, there is no convexity because you minimize something which is nicely convex, but with the constraint that you stay on the sphere, it's very bad. But it's this infinite dimensional setting, thanks to this concept of generalized flow, you restore a very nice convexity framework, which makes the problem quite tractable. So the fact that we are in infinite dimensional helps in a paradoxical way. So it's not that bad. And okay, and then because I have a lot of interest for numerical analysis, of course, you would like to see whether it's really consistent with the numerics that you can get from the fully discrete approximation. And unfortunately, so far, I don't think there is anyone has tried to prove that rigorously, but at least the numerical evidence is perfectly fine for me. So if you do that, for instance, if you do a discretization of the unit interval, not by, you know, I use 12 for but 12 is really not enough. So in order to have some kind of reasonable approximation, you use 144 in this picture. And you are drawing the trajectory. So actually, these are you know, that is like this tag permutation I show you. And of course, you cannot fix exactly the initial point and the final point because at the discrete level, it's still a permutation. It's still 1-to-1. So you just you just do a little window around the point you start with, and and then you see that it's already looking like the exact solution. And when you use more trajectory like 4,000 cube, it's very close to exact solution. So it's very reasonable theory if you think in numerical terms. Okay, and then you know, here in some sense, I show you the picture of trajectories starting from a very, very small area. But if you have to consider all the particles together, and then it becomes a mess because you have. But it's very nice because it looks like a vortex. It looks like a big vortex. So the particles are just moving around. So you are in 1D, but you have the feeling to be in a higher dimension in some sense. So you have a feeling of the rotation with in this one-dimensional setting. So in some sense, I think it's quite funny. And you can do. You can look at other data. For instance, here, the initial map X, and the final map is this one, the infimum of 2x, 2 minus x. So the map is like this, right? So which means that the first half of the interval stretch all over the final, the interval 0, 1 with positive orientation, and the second half is doing the same but in a reverse order. So I like to call that a Cherevino map because it looks like it. And then you see the effect of this map. Oh, very dangerous. So you see that if you look at the particle on the left side, they will invade the total interval in a smooth way, order-preserving way. And the other particle, you know, you have a reversing of the orientation, so they will cover also the full interval by reversing. And so you have this feeling of vortex. And in fluid mechanics, this can be, even if you are doing everything in 1D, this is a little bit like a potential flow on this side and a vertical flow with vorticity on the other side. And this is another type of solution. Actually, in that case, we don't know the analytic solution. But it's kind of numerical evidence that it should look very much like that. So it is a case where I don't know how to compute the solution, the exact solution, but there is a reasonably good theory for that. Okay, so now if I go back to the, now I would like to tell you the link with optimal transport. Because if I try to put the mathematical formula, I can, okay, let me put a complete slice at once. So if I denote by capital AI the grid points, so I have a discretization, for instance, for a cube, it's very simple. I take just a uniform lattice, and I call A sub I the grid points. And the unknown is really, you want to find L+1 permutation. The first one is, and the last one are given, sigma 0 and sigma n. Permutation of the endpoint. And so what is unknown is the intermediate step, and you fix the number of steps. So you need to fix the number of steps. So you have a number of time steps. So it's like in a numerical analysis. You fix the number of time steps. You fix the number of space steps. And you look for this intermediate permutation, knowing the initial one and the final one, and you just minimize the sum of the square. And so you have a distance, so this could be done in a Riemannian manifold if you want. So you have a notion of distance, so you could be Euclidean distance. And so here, for instance, you have the grid point for the permutation, the first permutation to the second one, and for all the grid points with the permutation sigma, and you do that for every time step. So it's a huge combinatorial optimization problem, which is very, I mean, which is very likely to be like an NP problem. It's very complicated. However, there is a strategy which is very natural if you're coming from numerical analysis. You don't try to solve that at once. You use a kind of iterative method where, assuming that you know you have a guess for all these permutations, for instance, you can update, for instance, the permutation number, well, that's not true, knowing the previous one, and you just iterate. Or you can do a Gauss-Seidel iteration, actually. It's even simpler. So in some sense, you can rephrase. You can say that this is like the discrete analogous of the Euler equation, in some sense, just to do this huge combinatorial problem. And so the strategy to do the iterative scheme is you have a guess for the permutation except one. So you are looking for the permutation at time step sigma k, at time step k, and you know all the other permutation. It turns out that in this functional, the permutation are just seeing their neighbors. So in some sense, to update the permutation of at the time step k, in some sense, you just need the information at time step k minus 1 and k plus 1, because the structure of the cost is very special. So the iterative method is much simpler because for every time step you have just to minimize something which depends only on this, which is known to you because it's an iterative scheme. This is known to you, and you have just to update that. And then you can rephrase that in a very simple way. So in some sense, what you want to do is to find a permutation sigma which minimizes this quantity, where Cij, which we call the cost matrix, is just given by this very simple formula, where here you have the grid point Aj, and Bi is just the average of the grid points given by the previous and the next permutation that you already know in the iterative scheme. So in some sense, this is known to you in the iterative scheme. So you have a Bi and Aj. So you have this cost matrix, which is given to you, and you just want to find the permutation that minimizes this total cost. And this is a very well-documented problem. So in some sense, I broke by iteratively, I reduced my problem to a succession of problems much simpler, which are like this. And this problem is very well known in combinatorial optimization theory. If you look at the book in combinatorial optimization theory, it's probably in the first 5 pages. So this is called the linear assignment problem, and it's a nice problem. Actually, it's a very nice problem for us, and very not interesting for the people in combinatorial optimization because it's a polynomial problem. So it's not NP. There is no mystery about it. So this is called the linear assignment problem. And the classical economic interpretation for manager, you have some it's a kind of caricature of management problem in economics. So you have n agents, and you have some tasks to fill, and you want to know what is the best assignment to do that. And you know the cost, you want to minimize the cost, and the cost is, you know that if the agent I is doing the task J, this will cost Cij. And so you try to see what is the best assignment between the agents. Okay? And this is called a linear assignment problem. So it's known in combinatorial optimization. It's not only it's polynomial problem, it's a very low order polynomial, it's n cube. So they can show that you can solve the problem in n cube operation. So you can see the discrepancy between the combinatorial optimization, because for them, the problem is very trivial. It's just n cube. So they would be happy with n to the 17 because it will be still a polynomial. But of course, in practice, if n is large, even n cube is really a lot. It's super costly. So for the real numerical analysis people, this is not acceptable. So you need to do that faster than that. And anyway, this problem is play a historical role because I think it's fair to say that this was really understood by Leonid Kantorovich in the 40s, actually, because actually he observed that this kind of problem is equivalent to a convex minimization problem. Actually, it's a linear programming problem. There is a hidden linear programming version of this problem. And this is typical of this kind of problem that, in some sense, you have a hidden convex structure in the problem. Yeah. And actually, it's quite easy to understand because there is a theorem which is due to Garrett Birkhoff that tells you that if you look at the set of permutation matrices, the permutation matrices are exactly the extreme points of a convex set, which is a set of all matrices with non-negative entries for which the sum of the line and the column add up to 1. So they are called bistochastic matrices. So it's a convex object, a convex set, and the extreme points are exactly the permutation matrix. So you can reduce the combinatorial problem to a convex optimization problem. And this is why it's quite simple and not so interesting from the viewpoint of combinatorial optimization. So this is a portrait of Kantorovich. And yeah, maybe the time is running fast, so maybe I could skip this. So just to show you an example of combinatorial optimization problem that looks almost the same, but now we have two. you have two matrix given matrix L and C, and you do that, so it looks almost the same. But this is an NP problem. So it looks very similar, but it's completely different from the combinatorial optimization problem theory. And but however, in a very interesting way, if you look at stationary solution of the Euler equation, of the incompressible Euler equation, the stationary means that the velocity field and the pressure do not depend on time. It turns out that if you discretize that, you can get this kind of problem. So even Euler, you know, you can say, well, I mean, Euler is related to a very trivial combinatorial optimization problem, but Euler is also related to a very hard combinatorial optimization problem. And I worked a little bit about this theory actually to see what we can do at the mathematical level for this problem. Okay, so now it's a little bit, it's a propaganda slide for optimal transport. This linear assignment problem in the continuous version was actually known for a long while, and actually I was addressed by Gaspard-Monge a little bit independently of Euler in 1780. And it turns out that the continuous version of the linear assignment problem, it's called the optimal transport problem, and this is incredibly connected to many parts of mathematics, essentially everything, as far as I know, almost everything. We have even number theory. And of course, very fashionable because, I mean, it has a lot of connection with data analysis and, of course, people doing artificial intelligence have a lot. There is a lot of connection with optimal transport. So it's a very useful tool. And in some sense, by letting in some of degeneracy of the Euler model, you end up with a very simple combinatorial optimization problem, for which the continuous version is extremely rich. So in some sense, with Euler, just going up and down, you know, from very difficult to very simple and very up and down, like this. So it's propaganda for the book of Cédric Villani, which is already quite old now. And there is a more recent work by Filippo Sant'Ambrogio, which is more like for applied mathematician. Yeah. But there are other books, of course, related to that. So I just, but they are good friends, some of them. Okay. But of course, there are many other books. Okay, so this is the connection with this guy. I mean, and Monge and now I have maybe a few minutes. I don't know. Yeah, not so much time. I guess I have like 8 minutes. I guess. Yeah, because and then I would like to tell you a little bit about a more recent set of work. So it took a while to me to be interested in that. So instead of keeping in mind this discrete approximation by permutation, because I like that very much, but I describe fully discrete geodesics. But in some sense, there is a trick to do a semi-discrete. So in some sense, you want to have a smooth evolution in time related to permutation. So it doesn't make a lot of sense, because you cannot define geodesics in a Riemannian geometry sense on a discrete set. It doesn't make any sense, because if you have a discrete set of points, how can you do that in a continuous way? But you can do it in approximately. It's a trick which is known. This has been, for instance, worked out in the smooth case by people like, I found this paper of 57, so very old, at the same time as the edition of the stamp showing Euler, actually the same year. And then the idea is to make a penalty method, penalty approximation. So you put a small parameter epsilon, and you look for geodesic curve in the standard way just by minimizing the square of the velocity. And then you just add a potential, which is a penalty potential for not being in the set of the configuration page, which is all the grid points up to permutation. So it's a representation of the permutation group through the grid points. So you look at all the, I use this notation A sigma. So A is the list of the grid point, and A sigma is the list of the grid point with a permutation of the label. And so you look at the discrete cell, the discrete set of all these possible permutations of the grid points. Okay, so this factorial n, so it's a finite set. And then, because of course it doesn't make sense to define geodesic, what you do, you put a potential, we tell you that the trajectory, which is supposed to be continuous, x sub t, will be as close as possible to this list of permutated grid points. So it's a kind of potential, which is defined as an infimum with respect to the group of permutation up with all the relabeling of the list of grid points. So I think it's rather simple, not too difficult to pick up. And now, once I do that, I am in a slightly more comfortable setting because now the time is continuous, so I can do calculus of variation in a more standard way. So for instance, if you want to look at a minimizing geodesic, approximate minimizing geodesic, it means that you are fixing the endpoints, x at time t0, x at time t1. X is a list of points in Rd of endpoints. So it's a huge space of finite dimension with Rd, where you are, for example, R3, if you want dimension 3, to the n, so the number of grid points. So of course, if you have 10,000 grid points, it's really a big space. And then you are trying to look a continuous curve on this big Euclidean space, and you try to be as close as possible to the grid point up to permutation. But of course, you need epsilon to be strictly positive, otherwise it doesn't make any sense. Okay, and then you can work it out by the standard calculus, because now you can minimize separately between, to get the optimality condition in x and sigma. It's not such a difficult thing to do, because if you minimize with respect to sigma, you get a discrete optimal transport problem, actually. Because it means that you are given a list of position, you have the grid point, and you try to select the best assignment between the grid point and the point. So this is really, for every t, you have to solve optimal transport problem, a discrete optimal transport problem. Now, when we minimize in xt, it looks very difficult, but no, because in some sense, at least formally, since the permutation is a finite set, at least, of course, you may have some catastrophic accumulation point, but usually what happens is the permutation will be fixed for a while. And therefore, if the permutation is fixed for a while, if sigma is fixed, this is a fixed number, it's a trivial problem because there is no minimization, it's just a quadratic minimization problem. So the optimality equation is trivial. So what is this one? So if you know the permutation, it's just a kind, it's not the pendulum equation because we have the reverse sign. So if epsilon was a negative number, this would be a pendulum. And you know, as long as the permutation doesn't change, it's very trivial to compute that. Because assume that you know sigma t. It's trivial. You get you don't get cosine and sine because it's a reverse pendulum. So it's hyperbolic cosine and how is it called? CH and SH. And now the other part is the optimization of the permutation. So at every time step, you are supposed to find the best assignment between the grid points and the position of the particle. So if you have a good optimal transport solver, a linear assignment problem, it's very easy to do, actually. And now the jump is in the framework of optimal transport, we understand very well what would be the continuous limit when n goes to plus infinity. So when the number of grid points is infinite, and what we get, so sorry, it's maybe difficult to understand with more explication, we get something that looks very much like Newtonian gravitation, in the sense that if x now is not a finite collection of points, but a continuum of points, so every point will be accelerated by a gradient of some potential phi, which is linked to the density of the particle. So the density of the particle is just so you know, when in the continuous limit, you can define the density of the particle. It means the probability of presence of the particle at some point. So this gives a density field, rho, And you compute, it turns out that in this optimal transportation calculus, you can compute the phi by solving this so-called Monge-Ampère equation, where you have the determinants of the identity matrix plus epsilon fois the Hessian matrix of phi is equal to rho. So it's a difficult PDE. It's a fully nonlinear PDE. However, it's very close to the Newtonian model, because if you assume that epsilon is small and you linearize the determinants, so the leading term will be 1 plus epsilon for the trace of the Hessian. So it is 1 plus epsilon Laplacian of phi. So you get Newtonian gravitation with, you have to remove 1, because in some sense this is like if you, when you work on the, for instance, in a periodic box, you have to remove the average density in order to do the calculation correctly. And therefore, you can see that as a nonlinear correction of Newtonian gravitation. So it's a kind of a funny output of looking at the incompressible fluid mechanics of Euler. It's to get some kind of and therefore now we have been working on that. And it turns out now optimal transportation they are a very efficient optimal transportation solver. And so in the Institut Astrophysique de Paris, they can do a Monge-Ampère simulation with 200, or maybe even 512 cubes, which is like 100 millions of particles. And they do that for cosmology for the early universe. And in this framework, a particle is a cluster of galaxies. So a particle, so you have 100 millions of particles. Each particle is a cluster is about 100 galaxies. So which means that you have an enormous amount of solar system in that. So it's really a very large scale type computation. So I don't remember which is exactly the size of the box, but the size of the box is of like maybe like 300 million years, something like that. And so this is a zoom on the box. And actually, we don't use exactly the combinatorial optimization device I was talking about. We use something which is actually more efficient, which is a semi-discrete approximation of that, which is due to my colleague Quentin Mérigot. And the 3D version has been done by Bruno Levy. And this is a really super large-scale calculation. And it's interesting, actually. You can compare with what we do, what you get with Newtonian gravitation. So we are quite excited about that at the moment. Okay, so so this is really the last slide. There is also something which is quite interesting, and it's a recent work that was started some years ago, but was completed recently with Émeric Barada and Luigi Ambrosio, which is to get this Monge-Ampère gravitation model, the discrete one, out of a purely stochastic model. So the stochastic model, you have a set of particles, and you assume that this is like a cloud of points, and you assume they are just moving by Brownian motion, independent Brownian motion. So no structure. So the particles, they don't interact. They are just indistinguishable, and they have all the same noise. And it turns out by a kind of 2 layers of deviation principle, large deviation principle, we end up with this model. So in some sense, it's hard to believe. So in some sense, so you get something which is more or less as complicated as Newtonian gravitation just by considering a totally stochastic model where you have a cloud of points. They don't interact, they are just independent. The only important thing is since they are indistinguishable, it means that their knowledge is up to a relabeling. And relabeling is permutation. So in this sense, there is a caution to do by the permutation matrices, and this is why we get in the limit some structure, and so we get something which is really a real interaction. So it's not Newtonian gravitation, but it's something very similar to Newtonian gravitation. And so in some sense, we have a physical model which is non-trivial out, and the starting point is pure noise. And I think it's quite interesting. I think in theoretical physics, people have some conjecture of this sort for even for the Einstein equation, but it's more it's not so clear. But however, at least for something which is almost a nonlinear version of Newtonian gravitation, you can do that. You have a kind of rigorous theory of that. And okay, so maybe I skip this nice picture. So this is like fusion of the Brownian cloud, and then in some zero limit noise, you see the order coming up. And then I would like to thank you. And so I don't know, I guess I just checked that yesterday on the web, so I don't know if you know this person. You know? Who knows this person now? You know?
The name starts with L.
Is what? Elena. Yeah, it's Elena Corter. Yeah, it's supposed to be the first woman who ever got a PhD here in Padova. So it deserves to be celebrated, right? I am correct? I am not. I mean, this is according to Wikipedia. Yeah. So thank you very much.
Thank you very much. So, time for questions, curiosities. Okay, I see that people is speaking.
Take your time. I need to do something.
Okay, you made a presentation which started with Euler and actually with a perspective that is very interesting, with a very simple permutation, and went, I would say, far beyond. Going back to Euler, which is still, it's of course an open problem. Is there a question that is still a dreaming question?
Because I didn't do a lot of analysis in this talk. In some sense, if you rely on the Arnold interpretation in terms of geodesics, for geodesics problem you have essentially two problems. You have the minimizing geodesics problem, where you are for instance, think about a Riemannian manifold on a sphere. So you have 2 points, and you try to see the shortest path. But there is another problem, which is more like I would say the geodesic completeness. So you start from one point in one direction, and you want to know how far you can continue the geodesics. So it will be locally minimizing, not globally minimizing, and there are 2 different problems. So the problem that people are interested in analysis is the second one. Yep. It's the initial value problem. So in terms of, so the velocity field is really like the direction you want to start with for the fluid. And you want to see whether you can continue this evolution forever. And this is the outstanding open problem for Euler equation. So to solve the initial value problem globally in time. However, there is also, from the geometric viewpoint, it's also interesting to look at the minimizing geodesic problem. So you know the initial position of the fluid, and you know but you don't know the initial velocity, of course. It's kind of control problem. And you want, in some sense, you want to recover what is the initial velocity leading to the final. And I would say that we have, at least in dimension 3 or more, a very decent, a very reasonable description by this method of which is a kind of generalized optimal transfer problem. So in the terminology of Figalier and Ambrosio, they call that I think they use this, the incompressible optimal transfer problem. So it's more sophisticated by the regular optimal transfer problem. It's more difficult actually. However, we have a rather good understanding of this minimizing geodesic problem. And what is left is a very difficult regularity issue for the pressure field. So in fact, there is a nice uniqueness result about the uniqueness of the gradient of pressure that connect 2 points by minimizing geodesics. So minimizing geodesics don't need to be unique. On Earth, you have okay. But the gradient of pressure, it's a theorem. If the dimension is at least 3, is unique. And it's kind of solution of a very, very degenerate elliptic problem. So the open question is, can we do some regularity theory for this problem? So after the work of myself, Ambrosio and Fiali, we have a limited understanding of the regularity, but it's not optimal. We are missing one space derivative to get, I have a clear conjecture that the solution, the pressure should be a semi-concave function. No more than that in the general setting. However, so far we don't know, so there is I think it's a very beautiful problem, but essentially nobody works on that, and including Alessio, I don't think he completely quit the problem. And I think it's a very beautiful, but probably very hard problem to solve. However, it's much more satisfactory than for the evolution equation. Because this trick, this convexification trick, is probably not good for the evolution equation. So it's something like maybe you know that for harmonic maps, there is a difference between the minimizing harmonic maps and the harmonic maps that are just, you had several concepts of harmonic maps. And then you have some, with one concept, for instance, in the harmonic maps in 2 dimensions, you have this work by Hélin saying that you have C-infinity regularity. However, if you use a different concept of harmonic map, you have a result by Tristan Rivière showing that you can get solutions that are nowhere regular. So in some sense, we are in this situation. So in some sense, the harmonic maps can be seen as a kind of toy model where you have a very satisfactory result when you are just minimizing, and it's very difficult when you are looking just for critical points. And the evolution equation for Euler is more like looking for non-minimizing harmonic maps.
Okay, thank you for this,
it's a very long
this
answer,
perspective.
sorry for that.
No, it's, I mean, it was a question that required a long answer. Are there other questions, curiosities? Otherwise, there is the 7th floor as more refreshment for who wants to join and ask by person other questions. Yes, hopefully you are coming. So thank you very much again for this very beautiful seminar.
Thank you. I didn't switch off because I don't